Namaskar. I am Sanjeev Agarwal and we shall be today discussing geometry. Geometry is of course one of the most ancient of all branches of mathematics. Geometrical figures are of course introduced to students at a very early age. By the time they are about 14-year-old, they are expected to be producing proofs in Euclidean geometry as well as to constructions. While proving theorems or doing constructions, the students face a major problem. The problem is, what assumptions can I make? What theorems can I assume? What theorems can I not assume? What results can I use to make my constructions? Is my construction valid? How do I prove that my construction is valid? As a teacher of geometry, I would like to be able to tell the student a bit about the history of the subject. What is Euclidean geometry all about? Who was Euclid? What did he do? How did he prove certain theorems? What are the assumptions that he made? And especially, what are the 5 postulates of Euclid? As we go along in this lesson, we shall be looking at Book 1 of the 13 books of Euclid's Elements. Out of the 13 books of Euclid's Elements, first 4 and Book 6 cover plane geometry. Book 5 is on ratio and proportion. Books 7, 8 and 9 are on theory of natural numbers or number theory. Book 10 is on irrational numbers, and books 11 to 13 are on solid geometry or 3D geometry. Euclid was born around 365 BCE in Alexandria and died in Athens, Greece around 300 BCE. Book 1 is broken up into 4 different distinct categories. The first category is definitions. There are 23 definitions given in the book. The second category is postulates. There are 5 postulates. These are the basic axioms on which the whole theory is based. The third category is common notions. There are 5 common notions. They allow you to compare measures of various quantities. Finally, there is the category of propositions, which are constructions, theorems, results. There are 48 of these. The 47th proposition is the proof of Pythagoras' theorem, and the 48th is the converse of Pythagoras' theorem. What we shall concentrate on in this discussion is some of the definitions, the 5 common notions, and the 5 postulates. The first definition given in Euclid's Elements Book 1 is that of a point. A point is defined as a geometrical quantity which has no length, no breadth, and no height. Definition 2 defines a line. For Euclid, any curve was a line. Definition 3 tells you that any endpoint of a line is always a point. The fourth definition characterizes straight lines amongst all lines. Definition 8 tells you what an angle is. Angle is when 2 curves or 2 lines lying in a plane intersect with each other. They form an angle. Definitions 9 and 12 tell you what happens when 2 straight lines intersect with each other. They form what is called a rectilinear angle. Amongst these angles, what are right angles? What are obtuse angles? And what are acute angles? For Euclid, straight angle did not exist as an angle. Definitions 15 to 18 give you the definitions of various parts of a circle. Definition 23 is probably the most important definition in this book. It tells you what parallel straight lines are. These are straight lines which are drawn in a plane and being produced in either direction never meet each other. The 5 common notions of Euclid are exactly what the name suggests. These are common sense ideas which allow us to compare measures of two geometrical quantities of the same kind. For example, they will allow us to compare the lengths of line segments, areas of two-dimensional figures, measures of angles, and so on and so forth. Common notion 1 tells us that things which equal the same thing also equal one another. For example, if lengths of the line segment AB and CD equal the length of the line segment EF, then their lengths have to be equal. Same thing with measures of angles. Common notion 2 tells us that if equals are added to equals, then the wholes are equal. This is a well-known standard practice that we use in manipulating equations. Common notion 3 tells us the same thing for subtracting equals from equals. That is, if equals are subtracted from equals, then the remainders are equal. Common notion 4 tells us that things which coincide with each other equal one another. What this means is that if we take a triangle and another triangle can be moved around so that it fits exactly on the same triangle, then its lengths are going to be equal. That is, lengths of the three sides are going to be equal and the three angles are going to be equal. The fifth notion tells us that the whole is greater than the part. That is, if we take a part of a line, its length is always going to be smaller than the length of the bigger line. If we take a part of an angle, it is going to be smaller than the whole angle. These 5 common notions shall be used along with the postulates to prove theorems using the definitions already stated. The 5 postulates of Euclid are axioms. Most of them deal with constructions. You do not prove that these constructions are valid. You cannot prove them. We shall be looking at these postulates one by one. The first postulate allows you to draw a straight line from any point to any point. What it means is that given any 2 points A and B, there is a straight line AB which has them as endpoints. Postulate 2 allows us to extend any finite straight line continuously in a straight line. We are allowed to extend a given line AB to CD. We may even extend it indefinitely in either direction. Postulate 3 tells us how to use a compass to draw circles. Given a point O and any line segment with an endpoint at O, I can draw a circle centered at O with its radius equal to the length of this line segment. I can also draw a circle centered at O and an unknown length. What I cannot do is draw a circle at a point with a length given somewhere else. That is, suppose AB is a line segment and O is a point not on this line segment. Then I cannot draw a circle centered at O, length AB. I cannot place my compass's 2 endpoints at A and B and take this up and bring it down to O and draw a circle. As soon as I lift my compass from the points A and B, the compass collapses. That this construction is possible is in fact proved as a theorem by Euclid. We will, in a later discussion, look at a proof of this theorem. The fourth postulate tells us that all right angles are equal to one another. The definition tells us that when I put a perpendicular upon another line, the two angles constructed are equal, and these are called right angles. It does not depend on the lines chosen. That is what the fourth postulate tells us. The fifth postulate is what we call the parallel postulate. This is the postulate which led to a massive amount of research. For centuries, mathematicians tried to prove that this postulate could be proved from the other four postulates. Ultimately, they proved that it was independent of the other four postulates. In fact, there exist geometries where the fifth postulate is false. What it states is that if a straight line falling on two straight lines, we call such a straight line the transversal, makes the interior angles on the same side of the transversal less than two right angles, that is, the sum of the interior angles on one side of the transversal is less than 180 degrees, then the two straight lines, if produced indefinitely, meet on that side on which the angles are less than two right angles. Several equivalent versions of this postulate have been given. Probably the most famous ones are by Playfair and Legendre, both given in the 18th century. Playfair's version is, for every line L and for every point P that does not lie on L, there exists a unique line M through the point P that is parallel to L. Legendre's version is, the sum of the interior angles in a triangle is equal to 180 degrees. In later discussions, we shall be looking at the propositions of Book 1. Namaskar.